All right, hello everyone, and welcome to my channel. This is an educational channel. We look at theories of everything, all-encompassing theories, magnum opuses from obscure authors, ancient and modern, and paradigm shifters, and really anything that can help you with your holistic approach to life. Things that you may never have heard of before, because they've been suppressed, but they are overall beneficial to your life. Today is our 406th video that we've done on the reciprocal system of theory from Dewey B. Larson. Larson was an engineer who lived in the 20th century, out in the Portland area mostly, and around 1959 he proposed his two fundamental postulates about the way the universe operated. He took those two postulates over the next 30 years and identified a theoretical universe. So this is Larson's universe. If his two postulates are correct, then the universe would look like this, is basically his theoretical universe. And then he compared his theoretical universe to the, the empirical universe of the legacy scientists, what they had measured in their laboratories about, what the universe looks like. And we're going over one of his books right now, just at the very beginning, called The Basic Properties of Matter. In this book, Larson theoretically derives many of the basic properties of matter, such as the boiling point and the melting point of different elements and compounds. And then he compares those with the scientific tables that have already been established. And so it's an interesting study, but it's a little bit difficult to get into. As we found out yesterday, we didn't even get through the first paragraph, because Larson a lot of times targets, in my opinion, the wrong audience for his work, and so he leaves you behind if you're kind of a lay person. So I'm trying to take the role of having to have gone through this work before and, had to stop after every sentence to figure out what he's talking about. I'm trying to be somewhat of a guide here. I think the first thing to do, though, is just to identify Larson's two fundamental postulates so we know where he's coming from. Basically, Larson is proposing a universe of motion. The universe is not made out of matter. It's not made out of energy. It is made out of motion. In fact, matter and energy are just merely kinds of motion. And in particular, Larson is referring to a kind of motion that he refers to as scalar motion. This is a kind of a non-localized, more generalized motion that you would envision if you were blowing up a balloon with dots on it. All of the dots are moving away from each other as you blow up the balloon. They're not moving in any specific direction. So that's a scalar motion. It's a motion that has a magnitude, but it has no particular direction. Every dot is moving away from every other dot. And that is part of his first postulate. The first postulate is where most of the action occurs. Also, with this universe of motion, motion is, other people have arrived at that concept before, the universe of motion, but they weren't able to make it work because they didn't define motion. Larson defines motion as the relationship between space and time. So that sets up a generalized reciprocal relationship between space and time. And just like all reciprocals, if you need, to jog your memory about what a reciprocal is. It's from your math class in like 5th grade or something. Reciprocal of 3 is 1/3. 3 over 1 and 1 over 3. They both have the same entities in them, but they're in different order. If you multiply them together, you get 1. So 3 and 1/3. Here we go again. Sorry very much about this. I've got to remember to stop doing this. Every night I'm recording at the same time, and I cannot figure out how to turn that alarm off. I'm not trying very hard, but yeah, I don't have a lot of free time. Okay, so 3 and 1/3, 4 and 1/4, 5 and 1/5. These are all reciprocals. And so reciprocals have the same qualities, but they're in different orders. So too with space and time. Space and time, basically motion is a fraction, with space or time as the numerator, time or space as the denominator. All of our scientific quantities are really forms of motion. But motion can have 3 dimensions. Larson calls that coordinate space and coordinate time. He has observed that space has 3 dimensions, x, y, z coordinates or volume in a still frame. And so by the reciprocal postulate, he also postulates that time has 3 dimensions in a still frame. And so you can get multiple dimensions in your, really up to 6, in your time-space coordinates of a fraction in of scientific quantities. For example, motion, speed is space over time. The bike is going 10 miles per hour, 10 miles of space and 1 hour of time. Acceleration, I dropped the rock out the window, it fell at 32 feet per second per second. 32 feet of space, 1 second per second of time, space over time squared. Turns out that energy is time over space. It took me 3 hours to move that thing 1 mile. 3 hours of 3 hours of time in 1 hour. 3 hours of time in 1 mile of space. And matter turns out to be time to the 3rd power over space to the 3rd power. Density, time to the 3rd power over space to the 6th power, because density is matter over volume. So time to the 3rd power over space to the 3rd power times 1 over times 1 over space to the 3rd power per volume, space per volume, or matter per volume, and so on and so forth. So what we have is a system that is self-checking. So you can check your equations and so on based on its space-time coordinates. But you also have what Larson calls clock time and clock space. This is the scalar motion part. As we identified with the balloon, space is always getting farther and farther and farther apart, but in no specific direction. Same too with time. Time is always getting later and later and later and later, but in no specific direction. So Larson refers to those as clock time and clock space. Then there is the aspect of discreteness. Time and space only come in discrete units. They are quantized, meaning that there is a minimum unit that you must have before you have anything. You have to have a full unit of space, and you have to have a full unit of time before you have space or time. If you have exactly 1 unit of space in 1 unit of time, Now, again, we said that space over time is speed. If you have 1 unit of space and 1 unit of time, you have what Larson calls unit speed. 1 over 1 equals 1. But unit speed turns out to be the speed of light. And this is the background speed of the universe. The universe is always moving outward at the speed of light in all directions. This is the empty universe. This is a universe with nothing in it. This is the 0 point of Larson's universe, or the neutral point, the null point. He calls it the progression of the natural reference system. This is omnipresent, always occurring. So this is a stark contrast from the legacy scientist universe, where they make their measurements from 0 motion. Larson makes his measurements from motion outward at the speed of light in all directions. Okay, that basically means half the universe is moving faster than the speed of light, which Larson calls the cosmic sector, and half the universe is moving slower than the speed of light, which Larson calls the material sector. Within each sector, there is also a subregion, because if you don't have a full unit of space, then you don't have space. That means that you are in time only. So within the material sector, Larson has what he calls the time region, and that is for atoms and molecules. Anything smaller than 1 unit of space, which is 4.56 times 10 to the minus 8 meters. The unit of time is 1.52 times 10 to the minus 16 seconds. And in the cosmic sector, you have what he calls the space region. If you don't have a full unit of space, then you don't have, if you don't have a full unit of time, then you don't have time and you only have space. And so that is the space region, and that is for cosmic atoms, or what other people would refer to as antimatter. Okay, now we started here reading this chapter 1 called Solid Cohesion. So he's referring to how different elements hold together in the solid state. And I guess we'll just start at the beginning, because we didn't get very far last time. The consequences of the reversal of direction in the context of the fixed reference system. Okay, that is the legacy science reference system. The reversal of direction that takes place at unit distance. Okay, that's 1 unit of space. Were explained in a general way in volume 1, which is called Nothing But Motion. That's another one of his books that we went over on this channel about 6 months ago. And so he's talking about phenomena that are occurring within the time region in less than 1 unit of space. And when you cross that boundary, the rules invert. The order of space and time invert. Just like when you cross into the cosmic sector, the rules invert. In the material sector, you have coordinate space, 3 dimensions of space in a still frame, and you have clock time. Clock is always getting later and later and later. When you cross that speed of light boundary, then you move into the cosmic sector and you get coordinate time, 3 dimensions of time, and clock space. Space is always moving farther and farther and farther apart. But within those sectors, you have the time region and the space region, and when you cross those boundaries, the rules also invert again. So that's what he's talking about, the reversal of direction that takes place at unit distance. We're explaining in a general way. As brought out there, the most significant of these consequences is that the establishment of an equilibrium between gravitation and the progression of the natural reference system becomes possible. Okay, so now the progression of the natural reference system we refer to as the movement outward at the speed of light in all directions. And that you can kind of model with the scalar motion of an expanding balloon. The balloon that you blow up, all the dots are moving away from each other. Gravitation is the opposite of the progression. Gravitation is as if you sucked in the balloon. All of the dots would be moving toward each other. Okay, the force field of gravitation is a misnomer. There is no field there. Not like there's no action at a distance. There's no everything is being drawn to this one, the center of the earth or whatever. There is just that each one of the locations is moving toward each other one of the locations. Okay, so that is the essence of gravitation. So these are opposite forces, but between the full, progression outward at the speed of light in all directions, and then gravitation inward at the speed of light in all directions, there is an equilibrium that is established, and that is really what Larsa calls the interatomic distance. Now, this same phenomena occurs outside the time region in the material sector as what he calls the gravitational limit. There is a location outside unit distance where the magnitudes of both of these motions are equal, the distance that we are calling the gravitational limit. That's really for astronomical phenomena. The sun, and that is an unstable limit. It's not an equilibrium. It's just an equality. For the sun, the first gravitational limit is like 3.61 light years. So within 3.61 light years, you're tending to move toward the sun. If you get outside of that limit, then you are going to be tending to move away from the sun. So it's an unstable limit. You either move toward it or you move away from it. But within unit distance, you're talking about an equilibrium. So here he says, but this point of equality is not a point of equilibrium. On the contrary, it is a point of instability. If there is even a slight unbalance of forces one way or the other, the resulting motion accentuates the unbalance. A small inward movement, for instance, strengthens the inward force of gravitation and thereby causes still further movement in the same direction. Similarly, if a small outward movement occurs, this weakens the gravitational force and causes further outward movement. Thus, even though the inward and outward motions are equal at the gravitational limit, this is actually nothing but a point of demarcation between inward and outward motion. It is not a point of equilibrium. Now he gets back to the region inside unit distance. In the region inside unit distance, on the contrary, the effect of, so this is the time region, the effect of any change in position opposes the unbalanced forces that produced the change. If there is an excess gravitational force, an outward motion occurs which weakens the gravitation and eliminates the unbalance. If the gravitational force is not adequate to maintain a balance, an inward motion takes place. This increases the gravitational effect and restores the equilibrium. Unless there is some intervention by external forces, atoms move gravitationally until they eventually come within unit distance of other atoms. Equilibrium is then established at positions within this inside region, the time region, as we have called it. Okay, so what you have to understand is that within the time region, there is a reversal of directions. So within the time region, the progression of the natural reference system is operating inward. and gravitation is operating outward. Gravitation tends to move things toward unit distance, and the progression tends to move things away from unit distance. And in this case, within unit distance, the progression is going to move things closer and closer together because that is away from unit distance. But in the outside region, outside of the time region, the progression is moving everything away from each other and also away from unit distance. Gravitation is moving things toward each other, toward unit distance. But inside the time region, we have a reversal of directions. So that is, again, kind of a misnomer of gravitation. We think of gravitation as pulling the atoms together. But it's actually the progression of the natural reference system that pulls atoms together, and gravitation that pulls them apart. These two forces arrive at an equilibrium, and that equilibrium is what Larson calls the interatomic distance. He hasn't gotten quite to that point yet. The condition in which a number of atoms occupy equilibrium positions of this kind in an aggregate is known as the solid state of matter. The distance between such positions is the interatomic distance, a distinctive feature of each particular material substance that we will examine in detail in the following chapter. So the next chapter, chapter 2. Here we're talking about solid cohesion. So, you know, we're on the same track. Displacement of the equilibrium in either direction can be accomplished only by the application of a force of some kind, and a solid structure resists either an inward force, a compression, or an outward force, a tension. To the extent that resistance to tension operates to prevent separation of the atoms of a solid, it is commonly known as the force of cohesion. So cohesion is the resistance of tension. So the tension tends to pull the atoms away from each other, and cohesion is the resistance to that force. The conclusions with respect to the nature and origin of atomic cohesion that have been reached in this work replace a familiar theory based on altogether different premises. This previously accepted hypothesis, the electrical theory of matter, has already had some consideration in the preceding volume. But since the new explanation of the nature of the cohesive force is basic to the present development, some more extensive comparisons of the two conflicting viewpoints will be in order before we proceed to develop the new theoretical structure in greater detail. Okay, now Larson is going to go into kind of a history of science approach, where he's going to look at this electric theory of matter, which is the prevailing theory of matter, and kind of poke holes in it, show how it's not as infallible as you might think. And then eventually he's going to show how his theory of cohesion is superior to this electric theory of matter. Okay, so the electrical, I hope you get an appreciation of how difficult this is for Larson. He's having to explain so many things at once just to get you kind of up to speed. So, you know, you can complain about maybe the way he's writing or how he's overlooking certain things or how he's not explaining certain things or passing over certain things. But it's a very difficult job to write paradigm shifting material, because the audience that you're going for, it needs to get up to speed, and in many cases they also need to unlearn what they've already learned. So, Larson is facing a gargantuan task here. We're still on the second page, and, he's already had to navigate about 10 different difficult maneuvers as far as, writing is concerned and conveying his message. Okay. So now he's going to get into the electrical theory of matter. The electrical or electronic theory postulates that the atoms of matter, of solid matter, are electrically charged, and that their cohesion is due to the attraction between unlike charges. The principal support for the theory comes from the behavior of ionic compounds in a solution. A certain proportion of the molecules of such compounds split up or dissociate into oppositely charged components, which are then called ions. The presence of the charges can be explained in either of two ways. One, the charges were present but undetectable in the undissolved material, or two, they were created in the solution process. The adherents of the electrical theory base it on explanation one. At the time this explanation was originally formulated, electric charges were thought to be relatively permanent entities, and the conclusion with respect to their role in the solution process was therefore quite in keeping with contemporary scientific thought. In the meantime, however, it has been found that electric charges are easily created and easily destroyed, and are no more than a transient feature of matter. This cuts the ground from under the main support of the electrical theory, but the theory has persisted because of the lack of any available alternative. Obviously, some kind of a force must hold the solid aggregate together. Outside of the forces known to result directly from observable motion, there are only three kinds of force of which there has heretofore been any definite observable knowledge: gravitational, electric, and magnetic. The so-called forces, which play various roles in present-day atomic physics, are purely hypothetical. Of the three known forces, the only one that appears to be strong enough to account for cohesion of solids is the electric force. The general tendency in scientific circles has therefore been to take the stand that cohesion must result from the operation of electrical forces, notwithstanding the lack of any corroboration of the conclusions reached on the basis of the solution process, and the existence of strong evidence against the validity of those conclusions. One of the serious objections to this electrical theory of cohesion is that it is not actually a theory, but a patchwork collection of theories. A number of different explanations are advanced for what it is. In all appearances, the same problem. For what it is to all appearances, the same problem. In its basic form, the theory is applicable only to a restricted class of substances, the so-called ionic compounds. But the great majority of compounds are not ionic. Where the hypothetical ions are clearly non-existent, an electrical force between ions cannot be called upon to explain the cohesion. So, as one of the general chemistry tests on the author's shelves, texts on the author's shelves puts it, quote, a different theory was required to account for the formulation of these compounds, end quote. But this different theory, based on the weird concept of electrons shared by the interacting atoms, is still not adequate to deal with all of the non-ionic compounds. And a variety of additional explanations are called upon to fill in the gaps. Okay, I think, okay, we're going to go one more paragraph here. In current chemical parlance, the necessity of admitting that each of these different explanations is actually another theory of cohesion is avoided by calling them different types of bonds between the atoms. The hypothetical bonds are then described in terms of interaction of electrons, so that the theories are united in language, even though widely divergent in content. As noted in Chapter 19, Volume 1, a half dozen or so different types of bonds have been postulated, together with hybrid bonds, which combine features of the general types. Okay, so I think he stated the problem here, more or less, that this electrical theory of matter does not explain non-ionic compounds. You have things like NaCl, and you have that's an ionic compound. But there's a bazillion of other kinds of compounds that do not rely on this kind of electrical valence type of situation. And they are still explained under this electrical theory of matter. He's going to go into that a lot more, but I think I was very much struck by this when I first read it many years ago, just how laughable this electrical theory of matter was in terms of explaining all these different kinds of chemical bonding, and that the vast majority of them have very, very little to do with valence, at least electrical valence, the way that I learned it when I was in chemistry class or whatever. So Larson will get into that a little bit more tomorrow. And I think you get to see the way he kind of picks apart the legacy theory, and then he's going to eventually show how his approach is superior. All right. Well, thanks for tuning in today, and have a great day.